Hello, everyone. I'd like to do a video on radio receiver. What is a radio receiver exactly? What does it do? Um, and so I'll give you a qualitative example what a receiver is, what it does, and we'll give an example, some examples with the FM broadcast receiver, something you should be familiar with, I imagine, to your daily life. Uh, and and there's a lot more to it than you probably ever would have thought. And then we're going to have go over 6 specifications that are commonly used to describe receiver performance. 3 of them that don't involve an interfering signal, and 3 of them that do involve an interfering signal. After all, the real challenge of a receiver is to process a desired weak signal while in the presence of strong interferers. So there needs to be some specifications on how to, how what a receiver is supposed to do with strong interferers present. So 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 video is kind of long, but it's broken into parts. So you can take it in chunks if you'd like. So on that note, let's get started. Let's talk about what is a radio receiver. Now we're going to differentiate, receiver. If you look it up in the dictionary, there's all kinds of different kinds of receivers that could be part of the trailer hitch on your truck, or in a financial business sense, a receiver has some meaning also in terms of if someone goes bankrupt, the court will appoint a receiver, I believe. Uh, but we're talking about radio receiver here for information transfer purposes. And why don't we limit ourselves here to wireless communications link also, uh, so that that would differentiate it from like a CAN bus or LVDS or I squared C bus or something like that, where you actually have a wired link. This would be a wireless link. So we were going to have electromagnetic radiation involved as the transmission vehicle, so to speak. So it's a block which recovers a signal from a transmission medium. And of course, we're going to assume wireless, like electromagnetic radiation is involved, and the receiver's input will be from an antenna of some sort that intercepts some electromagnetic radiation, and you have a small voltage input to your receiver then from that antenna. All right, now in the recovery of the information encoded onto the signal prior to transmission, the receiver will undo the transmit processing in reverse order generally. All right, now receiver has to do a whole lot more than that. It has to gain up a tiny input while also providing selectivity so that the other users of the electromagnetic spectrum do not interfere with your desired receive operation. And in some cases, the receiver will have to provide timing and synchronization uh, for coherent demodulation. Holy smoke! There's the receiver is really the heavy lifter here, not so much the transmitter. But in general, for instance, suppose if you're a data person, maybe you have a convolutional encoder, maybe an interleaver, and then a QPSK modulator, for instance, if you're talking about a data transmission system, maybe those 3 things. And then so you'd have an A, B, and a C here. So what are you going to do first after you receive? You're going to undo the QPSK modulator, and then you're going to, so that represents B minus 1, and just the inverse of this. You're going to undo the QPSK modulation, and then you're going to de-interleave, And then the third step, you're going to your Viterbi decode to undo the convolutional encode. And all of these steps are, in my opinion, a little more complicated than what you have to do at the transmitter side. So this is generally a big signal for half a megawatt for some old TV stations, to give you an idea. And then these are tiny signals here, input to our receiver. Okay. So then what? If we talk about a broadcast FM, let's do an example of broadcast FM here. All right. So in broadcast FM, this is going to be a frequency modulator, and this is going to be a preemphasis block, and so this would be a frequency FM detector or discriminator, they're sometimes called, and this would be the de-emphasis that undoes the preemphasis here. So what does this look like? What does this look like? What does our broadcast FM transmitter block diagram look like? Roughly, we're going to have our left channel. If you have two channels, again, most of these systems now are designed for stereo FM, but they still have to work for mono. And so this is, why don't we say broadcast FM example, why don't we say mono, okay? We add mono to that, okay? So that the mono radios still work, or if you only have a monaural input, just a single input, this would be where your audio comes in here. AGC, that stands for automatic gain control, and limiting. In the case the AGC fails, you have to limit the amplitude here, and we'll talk about why in a minute. Then we preemphasis, which is a block, which is really quite simple electrically. It's not a big deal, but it just shapes the audio from a frequency response perspective. So this number right here, you may not be able to read it very well, but that's just 2.1 kilohertz. And so from 2.1 kilohertz to 15 kilohertz, we have a 6 dB per octave increase in gain. So whatever the gain is at 2.1 kilohertz, for instance, you would have, if you go to 4.2 kilohertz, you'd have 6 dB more gain, 8.4 kilohertz, another 6 dB, and so on and so forth. So just a general high pass filter. It's flat up to 2.1 and then rises 6 dB per octave up to 15K. And then at 15K, we band limit the output. Okay, so that starts rolling off at, not any specified dB per octave, but probably, 3-pole low pass or something like that. Not a requirement in the standard. I don't believe that you have a certain low pass filter there. All right, but this is 6 dB per octave over this 2.1 to 15 kilohertz region. That's 6 dB per octave preemphasis. And then we go into our FM modulator. Okay, and by the way, just to give you an idea how simple this is, this network right here, this preemphasis network takes 2 resistors and a capacitor. What it takes to do that. And now it might take if you have a 3-pole low pass filter here for this band limiting, that would take 3 more capacitors and an op amp or 2. No heavy duty signal processing there. All right, now what is an FM modulator? An FM modulator is a block which has output like shown here. So if the output voltage is some amplitude, fixed amplitude, cosine of 2 pi t times FC, which is your carrier frequency, plus some Km constant Vm of t, where Vm of t is your modulation voltage, your audio, in other words, your shaped audio, your preemphasized audio, Vm right here. That's the input to the frequency modulator. So I think maybe you can see, without doing a lot of heavy-duty algebra, that if Vm is 0, then we just have cosine of 2 pi fct, or cosine omega ct, and that's your carrier. That's what the FCC licenses you to transmit on. That might be 90.1 megahertz, for instance. That would be your, if you're KERA in Dallas, your licensed frequency is 90.1 megahertz. And then Vm of t is your audio input. And again, Vm0, F equal Fc, carrier frequency. Now let's suppose if your Km, this modulation constant here, was 25 kilohertz per volt, then your Vm of t would need to be limited to plus or minus 3 volts for a maximum deviation of 75 kilohertz. Now, FCC limits you, Federal Communications Commission limits your broadcast FM stations to 75 kilohertz deviation, which means that if you don't want your frequency out of your frequency modulator here to be off by more than 75 kilohertz from your desired FCs, your center FC, then you have to, for this Km, you'd have to limit your Vm of t to plus or minus 3 volts so that you don't exceed 75 kilohertz deviation, because that's what the FCC rule is. And that's why you need this block here. This block must have AGC, automatic gain control, to adjust the gain of your audio path, and then in case the AGC can't react quick enough, a hard limiter there, so that this voltage is not so high that you have too much bandwidth coming out of your FM modulator. Now, note that this particular system is a little unusual, maybe, in that the bandwidth of the output is determined more by the voltage here than it is by the frequency here. So you can easily, and when you have a 1 kilohertz modulation frequency here, have 75 kilohertz deviation here, just depending on what the amplitude is of the voltage here. And when you speak softly, when the announcer speaks softly, this would be a low voltage. When he speaks loud, this is a large voltage. The deviation here is small when the audio input is low. The deviation here is large when the audio input is larger. And the power amplifier would gain up the output of the frequency modulator, and then you go into a low pass filter, filter off the harmonics, and then up the tower you go at some frequency around 100 megahertz. Now, note that you can have octaves of bandwidth here. Octaves of bandwidth. You go from 50 hertz all the way to 15 kilohertz, that's more than 8 octaves of bandwidth. All right, so then you go through this process right here, and now you're 100 megahertz, something on the order of 100 megahertz, plus or minus 100 kilohertz. It's almost single frequency at this point, super broadband here, okay? And then this approach allows multiple access. For instance, you can have multiple users in the same band transmitting on different frequencies, and then the job of the receiver is to choose which one you listen to. Okay? Now, again, I think we already stated about the 75 kilohertz deviation. That's a limit, and I'm not saying that the Km is 25 kilohertz per volt. That's just an example I made up. Okay, the bandwidth on the output is 180 kilohertz. That's the typical bandwidth for commercial FM, broadcast FM, 180 kilohertz bandwidth, plus or minus 100 kilohertz, within plus or minus 100 kilohertz of the carrier frequency. FCC allocates 200 kilohertz per radio station. The channels are on 200 kilohertz centers between 88 and 108 megahertz. Okay, so that's a little bit about broadcast FM. Now, what about the receiver that picks that signal up and processes it? All right, what about the receiver? from a system view, we got RX analog processing in this block. We have 180 kilohertz bandwidth here. This would typically, most FM receivers, be 10.7 megahertz at this point. The IF input to the detector, 10.7 megahertz, about a volt peak to peak. 180 kilohertz bandwidth. That we have selected a particular channel, a particular radio station, 180 kilohertz bandwidth. That's the bandwidth here. We go through our FM detector. Now we're audio. We recovered our audio and noise, of course. And now we go into our de-emphasis block. So remember, pre-emphasize and then FM modulate in the transmitter. In the receiver, we undo the FM modulator here with the FM detector, and then we de-emphasize. And remember, in the transmitter, starting at 2.1 kilohertz, we pre-emphasize 6 dB per octave on the uphill slope. In the receiver, we de-emphasize with a 6 dB per octave down slope between 2.1 kilohertz and 15 kilohertz. That gives us a net flat audio response from very low frequencies up to 15 kilohertz. Now, this is the big improvement that FM has over AM radio, and that has wider bandwidth for for fidelity. It actually gives you 15 kilohertz of bandwidth instead of AM, which is like 5 kilohertz, and better signal to noise ratio too. So again, this now is 15 kilohertz bandwidth, and then we go into your audio stages, which are adjustable gain. So volume control, in other words, how much audio do you want? Okay. Now, in some cheap receivers, you may not even see this extra band limiting here, in that the audio stages themselves just do that. You might not actually have a circuit in there to do that band limiting. You just see the de-emphasis. The de-emphasis will be there for sure, because that is free. It's a single resistor capacitor network that takes to do that. This standard low pass filter with a 2.1 kilohertz corner. All right, so again, the receiver should undo the processing done in the transmitter in reverse order. In transmitter, we pre-emphasize first and then modulate. In receiver, we demodulate and then de-emphasize. The net result is a flat frequency response, but we get about 7 dB of SNR improvement for our trouble. And the reason why this gives you a 7 dB SNR improvement is because the noise coming out of this detector is not flat. It's parabolically shaped like a bowl, okay? Parabolically shaped, so as you go up in frequency, the noise level increases. This flattens that out and attenuates that high frequency, that noise at high frequencies. This undoes that. And of course, it would also mess up the frequency response of your desired audio, but not if you pre-emphasize at the transmitter. All right, so that's why we do the pre-emphasis and de-emphasis. You get a net 7 dB SNR improvement. And the FM, this wideband FM, also gives you some SNR improvement, so you can get a considerably better, SNR from FM than they could from AM, and that's why most everybody migrated to FM, and you don't see music on AM anymore. Okay, so most all of the real work in the receiver is done in the receive analog processing block. This block must extract the desired small signal from a sea of noise and other interferers, gain the signal up to about 1 volt peak to peak for the detector. Now think about how much gain that is. This signal here at the input to the might be minus 110 dBm maybe, and we're going to take and gain that all the way up to 1 volt by the time we get to the FM detector. That's a lot of gain in this lineup. Now, so what is some of the stuff that we might see in this RX analog processing block? A lot of amplifiers, you can be sure of that. Always should have some kind of selectivity up front to limit how much garbage you let into your RF amp. All right, an RF amplifier, a mixer, because this is a super heterodyne receiver. We do not try to tune this filter to have this filter have a bandwidth of 180 kilohertz and tune it to the particular radio station. That is virtually impossible to do that. So the way the super heterodyne receivers work is you have a fixed filter here at an IF frequency. This would be at 10.7 megahertz usually. A fixed filter at 10.7 megahertz or some other fixed IF frequency. And this filter can be 180 kilohertz bandwidth. And then we shift the band down so that your desired radio station you want to listen to lands at 10.7 megahertz, and the rest of them get filtered off. The rest of the band gets filtered off. So we actually tune this receiver mostly by changing that oscillator frequency. That's how you tune this receiver for the biggest part, is by changing that oscillator frequency, because that determines where the radio station that you're wanting to listen to lands with respect to this 10.7 megahertz IF here. This filter here is also tunes depending as you tune the receiver, but not it doesn't have very much selectivity. You need this filter for other things. Okay, super heterodyne, very, very great leap forward in receiver technology. Early 40s AM radio receivers, in some cases they tried to do tuned radio frequency. Nightmare, mechanical nightmare trying to tune a lot of LC filters across the AM radio band. And the super heterodyne was a giant leap forward. Even digital receivers have this super heterodyne concept here. So we shift the band down, shift the whole band down, and then you adjust this oscillator frequency such that your desired radio station lands on this filter, and then the rest of the band gets filtered off. Well, for an example, if your desired radio station here was 100 megahertz, and actually I think the FCC doesn't allow 100 to be 100.1, but let's say it's 100 for just for easy math, then this oscillator here would be 110.7 megahertz, such that 110.7 minus 100 equals 10.7, and your desired radio station goes sailing through, and the rest of the band gets filtered off. And the reason why we get that differencing process and that this mixer here implements what we would like ideally to be a multiplier, which is why it's shown looking like a multiplier. And we're taking advantage of the fact that the product of two cosines, where this is cosine of one, this is cosine A here, and this is cosine B coming in. The product of two cosines is half the cosine of the sum plus half the cosine of the difference. And so the sum frequency gets filtered off. The sum frequency is up to 200 and some megahertz. The difference frequency is your 10.7, and that's what propagates through the IF to the FM detector. And then of course we have our de-emphasis and band limiting, which we've already talked about, and our audio. Now, one last thing, kind of a little interesting property, because there is no information in the amplitude of an FM signal. It's all in phase or frequency. The FM radio will have a limiter at the just before the detector. All right, so that strips off. In other words, it's some kind of a circuit that's jammed into compression really hard, so that when the input changes amplitude, the output doesn't change in amplitude, and then that removes amplitude information and makes our receiver not as sensitive to AM, because this is supposed to be an FM receiver. So you don't really want clicks and pops from lightning storms and stuff like that. to be causing clicks and pops in your audio here. So this limiter helps protect the detector from AM, which wasn't supposed to be there, which would be there because of Mother Nature. Okay, so that is what it basically we have in our analog processing block from here to here. There's your antenna. That's what's in the analog processing in a broadcast FM receiver, typically super heterodyne. All right, so we're going to pick up in a minute. We'll talk about some of the specs that you might have on an FM receiver. Not that you necessarily do on broadcast FM receivers, but some of the things that if you care about if you're a receiver designer. Okay, now let's look at some of the receiver specs that you might see on a receiver. That you won't see some of these on broadcast receivers, but on more commercial receivers, you have some of these specs. Most of these specs, in fact, on commercial receivers. So first on the list, or let's focus first on the ones that don't involve interferers, just the desired signal. And the first on that list, and one that you probably are familiar with, is sensitivity. So what is our definition of sensitivity? Well, it's the measured signal level required at the input here. You disconnect the antenna and connectable signal generator probably, for a specified output signal quality level over here. And the noise figure would be the relevant radio design parameter that would affect sensitivity. You improve noise figure, you improve your sensitivity. All right, so and by the way, we did talk about noise figure in a previous video. You can look at that and see how to figure cascade noise figure, what noise figure is, even a calculation of a noise figure of an amplifier. Okay, so there's that in another video. So but one of the important things is that you have to know before you can even think about assigning a number to your sensitivity is what do you want for the quality of the output here. The more quality you want on the output, the more you're going to have to put in on the input. So that is goes without saying, I guess. So for an example, let's pretend or suppose that we have calculated our system noise figure for our entire lineup here, and it's 8 dB. Not super great, but not super horrible either, I guess. 8 dB noise figure, and that we want SNR at the output here of 40 dB, which is pretty good, 40 dB SNR. Now, we know that we're going to get 7 dB improvement from our preemphasis, not predistortion, preemphasis, and de-emphasis, of course, together. So we really need 33 dB SNR at the detector output here, effectively. What do we have to put into the detector to get 33 SNR out? And that would be the question. So if you go to Taub and Schilling, Principles of Communication System, Chapter 10, Equation 6-16, suggests that about 17 dB SNR here for 33 here. All right, 17 dB here. All right, and now, since so we need 17 here. Now, our receiver noise figure is 8 dB, and the definition of noise figure is SNR in divided by SNR out. And we know this is 17, and we know this is 8 dB. So what SNR in do we need? And the answer would be 25 dB. 17 plus 8, 25 dB. All right, so now figuring our receiver sensitivity then, SN divided by KTB, Boltzmann's constant times temperature times our bandwidth, which we're going to use 15 kilohertz here. And I believe that's the way Taub and Schilling had intended it to be. By the way, there's that potential point of confusion is certainly here the bandwidth is 15 kilohertz, because most of the people wouldn't express a low pass bandwidth as being double-sided. Even though it's really plus 15 kilohertz to minus 15 kilohertz, you might say that's 30 kilohertz. But most of the time, you would describe a baseband bandwidth like that as from 0 to whatever the upper frequency limit is, not from minus 30 or 15 to plus 15, for instance. So you go from 0 to plus 15 kilohertz. All right, but back here in the IF, to support that 15 kilohertz audio bandwidth, you need 30 kilohertz because it's double-sided. However, I believe the way this equation is written in Taub and Schilling is that that's supposed to be a 15 kilohertz bandwidth here that you plug in for the B there, KTB, and then just working in dB instead of, so you don't have to divide and multiply here. Our SN is going to be our 25 dB SNR that we need, minus 1674 dBm per hertz. That's KT. All right. And then 41.8 for 15 kilohertz, and then adding those up gives us minus 107.2 dBm for our sensitivity spec. All right, so that is I think that's about all we need to say about sensitivity. All right. Okay, let's talk about hum and noise. It's another spec on a receiver. It's important. So what is it? It's a measure of the residual audio output on the from the receiver when you have a large unmodulated signal at the receiver input. So you expect to have nothing coming out of the audio output, but there will be stuff, and that gets rolled into hum and noise. So what are the metrics that affect this hum and noise? Is the close-in phase noise and spurious on the oscillator. So that's this block right here. This guy is your important block to pay attention to when you're worried about hum and noise. And its power supply. The power supply to this guy, and the power supply to this buffer here following the oscillator, and maybe even some of the low-level audio stages here, their power supply input. If there's this garbage on it, that'll affect your output. But most important is that oscillator right there from a power supply cleanliness perspective. So, and then close-in phase noise, and we'll see that. Okay, so now when doing a hum and noise measurement, what are you going to do here? Now, you certainly read the spec or the standard, read it, and read it carefully. Do what it tells you to do, or the number that you get won't mean anything. Now, when doing a hum and noise measurement, you're going to take a reference audio power measurement, and I'll tell you what to do. You'll just tell you a modulation frequency and a deviation. Let's say 1 kilohertz for the modulation frequency and 75 kilohertz for the deviation, because this is broadcast FM. Okay, let's say. And then you're going to turn off the modulation on that, or you're going to take a power measurement with this reference case. So power measurement, what's coming out of the audio power measurement. And then you're going to shut off the modulation on this generator, and then take another power measurement. And then hum and noise is the ratio of those two powers expressed in dB. All right, so an example here then. With the sensitivity spec that we developed previously, where we wanted 40 dB output SNR, you would probably want to have your hum and noise spec be at least 50 dB, or your hum and noise will affect your sensitivity measurement. Certainly, if your hum and noise is less than 40 dB, you'll never ever get to 40 dB SNR when you try to measure sensitivity. So that's kind of, common sense, I guess, but you got to have the noise floor with a strong signal lower than what you need the noise floor to be when you're doing your sensitivity measurement, or you'll never be able to pass your sensitivity spec. So let's assume that we might like to see about a 50 dB hum and noise spec, and so now how would you determine what you might expect for your hum and noise spec? And it certainly depends on what kind of a receiver you're trying to design and what kind of oscillator you got. So here I found a crystalline microwave oscillator, and this one is 136 to 174 megahertz. It tunes data sheet. And this is not what you want for this receiver, but I just use the phase noise table because this is a low noise oscillator, they said, and so here is the phase numbers that the phase noise numbers as they publish in the data sheet for this crystalline microwave CVCO 55FL VCO, voltage controlled oscillator, is what VCO stands for. So at 1 kilohertz, it was minus 88.6 dBc per hertz. At 10K, minus 120.6 dBc per hertz. That means dB below the carrier. That's what dBc means. So if my carrier power was 0 dBm, then my noise power at 1 kilohertz offset would be minus 88.6 dBm in that 1 hertz bandwidth. Okay, that's what that means. Minus 88.6 dBc at 1K, minus 120.6 at 10K, minus 142.8 at 100K, minus 160 at 1 meg, and minus 165 at 5 meg. All right, this is supposed to lay a low noise VCO. Now this region right here is this 1 over F noise limited region. We talked about that in the noise video. We talked about how 1 over F noise affects the low frequency of audio circuits, but it also affects oscillators because it gets mixed up and ends up around the output of the oscillator as noise. Okay, so you can see here in this 1 over F region and lower, by the way, they don't give you specs less than 1K, but that 1 over F region extends lower in frequency also, of course. And you notice that we have got about 30 dB reduction in noise here over this decade from 1K to 10K. And then from 10K to 100K, we have about 20 dB, minus 20 dB per decade over these two decades here, roughly. Minus 20 dB per decade. That's the thermal region where you'd expect your oscillator to do just based on the thermal noise. And then this minus 165 is the floor. Okay, so we need to be able to integrate this 1 over F noise in that low frequency region, even less than 1K. And so we need to figure out how to express what this phase noise is in this region, rather than just have be discrete data points in a table. So we know that this L of F, with this phase noise here, is equal to some constant divided by F cubed. All right, that's what corresponds to the 30 dB per decade roll off. So we just need to find out what C is here. And well, we know what our phase noise is at 1 kilohertz. It's 10 to the minus 8.86, I guess. That's what our phase noise is at 1K, and plugging in 1K here, we can solve for C. So L of F equals C over F cubed equals C, in this case, over 1K cubed, also equal to 10 to the minus 8.8. I believe I didn't put the 6 on there, minus 8.8. Probably should be 8.86, but I think I just used 10 to the minus 8.8. And now, of course, we can easily solve for C. C ends up being 1.5. So our L of F here, phase noise, is 1.5 over F cubed. And again, if you want to plug in, for instance, 10 kilohertz, you plug in 10 kilohertz for F, and then take 10 log of that, you should get something close to this number right here. It's not exact, right? Because this delta right here is a little bit more than 30 dB, and what we assume when you write this, you're assuming it's going to go exactly 30 dB per decade. All right, so now we have an expression for what L of F is in terms of F, and something we could integrate. And it's a real easy integral to do, so don't panic. All right, so now we got one more little stretch to do here. We don't really care about the integrated phase noise. That'll give us a phase if we integrate that, a radian squared if we integrate phase noise. What we care about is delta F, deviation. Why? Because this block right here, the detector block, turns deviation into volts. All right, so we know that 75 kilohertz deviation resulted in a certain number of volts here, and that was our power reference. How many hertz of deviation does the noise from the oscillator make here? We know what our deviation is here. We can find the voltage, and then the ratio of those two voltages would give you your hum of noise. Okay, that's what we're going to try to do here. So what we have to do now is not find our phase noise, but we need to find our deviation. And for FM, deviation delta F equal beta FM, where FM is your modulation frequency, beta is your peak phase excursion, and delta F is your deviation. Now, beta squared here corresponds to the phase noise dBc value. So this number relates to beta squared at 1 kilohertz, for instance. So let's just do a calculation, for instance, just at 1 kilohertz, just to see what this means. So at 1 kilohertz, our phase noise is minus 88.6 dBc, which is equal to minus 10.10 to the minus 8.86, which is equal to beta squared. Beta, where beta is this beta here, the peak phase deviation. All right, I know this is a little confusing, and we're not really explaining this, but I want to. So now we don't want beta squared. We want delta F squared. So how do we get delta F squared? Well, beta squared FM squared, of course, is delta F squared, and so delta F squared at 1 kilohertz would be F squared. There's our frequency. And there's our beta squared. That's the phase noise here. And so that works out to be 0.0014 hertz squared. Now that's from that little tiny bit of noise right there in a 1 hertz bandwidth at 1 kilohertz. That little tiny bit of noise in a 1 hertz bandwidth at 1 kilohertz offset from the oscillator would result in a 0.0014 hertz squared deviation squared. That's what we care about. So now what we need to do is integrate. We want to know all of the noise that we're going to have, not just from that little 1 hertz bin. So we can integrate and find the total delta F squared from the noise. And it's an easy integral to do, so don't panic just yet. So what are we going to do? Here's our L of F, 1.5 over F cubed. We derived that on the previous page. We know our delta F squared, deviation squared, is equal to this. That's our beta squared times F squared, modulation frequency squared. So that ends up being 1.5 over F. And so we're just going to integrate 1.5 over F over whatever range that we want to integrate. Now I'm going to integrate from 10 hertz to 2.1 kilohertz. 10 hertz is judgment. Okay, depends on what kind of audio bandwidth you got. If you want to go, if you're sure your audio doesn't go down that far, then you may not have to integrate down to 10 hertz. I mean, remember that the audio doesn't roll off like a brick. The audio starts rolling off at whatever the corner frequency is, but it doesn't have infinite attenuation. When you go less than that corner frequency, it just starts rolling it off. So anyway, it's judgment on what you use for the lower corner, and for the upper corner, 2.1 kilohertz I used for a reason we'll explain in a minute. And then so we're going to integrate 1.5 over F between 10 and 2.1 kilohertz. And that ends up being 1.5 times the natural log of 2100 over 10, which is equal to 8 hertz squared. Okay, that's our deviation squared from that whole region. And remember, at 1 kilohertz, we had 0.0014 hertz squared. And so if we integrate over this whole region here, we get 8 hertz squared. That's not too bad. Pretty good. So what would we compare that to? Well, you can either take the square root of that and compare it to 75 kilohertz and then take 20 log, or I just took 75 squared divided by 8 and then took 10 log of that, and I got 88.5 dB. Okay, so again, you could take 20 log of 75 over the square root of 8, or you can take 10 log of 75 squared over 8 and get this, 88.5 dB. So we're in no trouble with hum and noise from the oscillator's noise for this oscillator and this wideband FM system. But I'm wanting to tell you, you get into some of the narrowband FM systems, look out, because suppose you were working on some of the stuff we used to do, that where your test deviation would be 3 kilohertz instead of 75 kilohertz. Narrowband FM systems, 3 kilohertz deviation. Well, now you're not going to be getting 8. You may have the same oscillator phase noise, but you only got 3 kilohertz deviation for your reference. You're not going to be doing so good. But not a problem though for this wideband FM. That's why we have wideband FM, because the larger deviation gives you a larger audio output, and all these little noise sources are less significant. Clicks and pops, everything's less significant compared to a large audio output relative to a small audio output. All right, now why did I stop at 2.1 kilohertz? On the high side, the integral stopped at 2.1 kilohertz, because that's where the de-emphasis starts to kick in. So even if you think you need to go beyond 2.1 kilohertz, you got to do a different integral. Because now you got another filter kicks in and starts rolling off the noise. So so and then so if you really wanted to go farther, you have to go from like 2.1 up to 10. Okay, with that de-emphasis filter kicked in, and then you change from the 1/f region to the thermal region where your oscillator rolls off less quick, and so you really need to start a new integral there too. But it doesn't matter. The phase noise of this oscillator is getting so good so fast, plus the extra protection you get from the de-emphasis filter. So there's no additional degradation from the region above 2.1 kilohertz. But probably didn't even really need to go up to 2.1 kilohertz either. It's the low frequency stuff that dominates this. Now, what about the power supply? Now, this is so simple, but holy smoke. Suppose our power supply ripple, say 120 hertz or switching spurs or whatever it is 1 millivolt peak to peak. Millivolt peak to peak. For this oscillator, the CVCO55FL, the one we've been looking at, the power supply sensitivity spec is 1 megahertz per volt, worst case. And if I change the supply by a volt, 1 megahertz frequency change. 0.5 megahertz per volt typical, 1 megahertz per volt worst case. If I take this 1 millivolt peak to peak times that, I get 1 kilohertz peak to peak deviation on my oscillator from power supply ripple. Now we had 8 hertz squared from all the noise. Here we have 1 kilohertz, not squared, peak to peak deviation from power supply ripple from 1 sinking millivolt. Okay, now you know hum and noise. We figured the noise. Here's the hum part. If you have a sinusoidal ripple like this, that's going to be here you have 1 kilohertz peak to peak deviation, and our peak to peak reference deviation would be 75 times 2, 20 log of that, 43.5 dB. So there's what you need to pay attention to big time. In general, if you can measure the ripple, you're in trouble, especially for some of the narrowband stuff we used to work on. We had 2 power supply. We had one regulator and then another regulator regulating the regulator output before you got to the VCO. Okay, and the power stage. If I find my little sheet here. Second here. This buffer right here. That buffer needs a clean power supply too, because if you modulate its bias, that changes its input impedance a little bit, and that'll load pull the oscillator. So this and this both need a clean supply. You want a high spec receiver, you gotta do everything right. Okay, so that's hum and noise. Now we spent a little more time on this one than probably we will on most any of the specs, because you had to do an integral, and just wanted to give you a flavor for how important that oscillator is. The super heterodyne receiver. The super heterodyne receiver is absolutely fantastic in what it offers you, in the ability to use one IF filter for everything. But holy smoke, you have to have a good oscillator, a really good oscillator. And we're not done talking about the oscillator yet. It causes other problems. And the mixer, a good oscillator and a good mixer to have a good super heterodyne receiver. Okay, let's talk about distortion. This is one of the metrics. This will be our last metric that doesn't involve an interferer. Just a desired signal only, you can have distortion issues. So let's go over a qualitative overview of some of the sources. It's a little hard to put numbers on these things, but I think in your audio stages, you can certainly understand clipping. Most of you have probably had some experience with that one time or another, which is just you drive a stage too hard, or it's not biased right, or some combination of the two. And instead of having your sine wave output, you get a flat top or flat bottom or both, just associated with too much level clipping. And that any amplifier will do that if you drive it too hard. In some cases, it looks worse than that. Crossover distortion is another type of distortion that an amplifier can do. And this is distortion right around the zero crossings, where the easiest way to get this is if you try to build a complementary symmetric emitter follower and don't bias up the two stages to keep them both on all the time, then for instance, your input would have to come up to 0.7 before you even turn on the NPN, and it has to drop down to minus 0.7 before you even turn on the PNP, and then you have that region right there where it's zero. And so if your audio inputs are low enough, you'll get no output at all. If your outputs are big, you get distortion. You don't notice it as much, but be super bad at low levels, and that's crossover distortion. Now, on the other side of the audio distortion issue, with lots of negative feedback in some of these commercial or consumer audio amps that people buy, they'll claim maybe 0.01% total harmonic distortion. And that's because they build effectively a big power op amp with lots of negative feedback, and you can get really low total harmonic distortion measured with a sine wave. And this is specsmanship. It doesn't really buy you anything, and in fact, it may actually not be good for real world distortion from like large input levels. This negative feedback can cause waveform distortion when you overdrive it, and it can be worse than the clipping. And it's just a specsmanship issue, and it applies to the audio only, not to the FM receiver part. So, many amplifiers you buy, you'd have the ability to use your receiver, for instance, as an audio amplifier for other pieces of audio equipment. When you're actually using it as the audio amplifiers that come with it to amplify the FM receiver, the FM receiver's distortion will be significantly larger than numbers on like 0.01%, which you don't really need anyway. So now, what about the FM receiver? Filter amplitude flatness. This filter here, this IF filter, that filter obviously needs to be 180 kilohertz bandwidth, and its amplitude needs to be reasonably flat over 180 kilohertz. And if it's tilted or too narrow, or if the radio is mistuned so that half of your energy is hanging off the end, that'll certainly cause distortion. And I don't really, I've never seen it quantified, put numbers on it, but it'll certainly cause distortion, filter amplitude flatness. Now, something that you wouldn't have maybe thought of is filter group delay flatness. So if you have a high performance IF filter, it can have a very nice rounded nose like I'm showing here, but the time delay through this filter can be several microseconds more at the band edge. Like for instance, if this is 10.7 megahertz right here in the center, and this is maybe 10.78 and 10.62, the delay at these frequencies can be several microseconds more than the delay in the center of the band. Now, if obviously what you would like is all of the spectral components that the detector needs to put the waveform together put the waveform back together again, so you get a sine wave output. If they don't get to the detector at the same time, that's not going to be good for distortion. And again, I don't know how that I've ever seen anybody try to calculate what is to put numbers to it in terms of what is the percentage distortion associated with a certain amount of group delay distortion. But I do know that some people have even investigated having two IF filters, one for cases where you really need the selectivity and where you're where you're getting interfered with by somebody, because group delay distortion will cause some low level of distortion, but there's no distortion worse than having an adjacent channel interfere that's not removed by your IF filter. That's horrible distortion. And so you need a narrow filter sometimes, and then if you have a situation where you don't have an interferer, a wider filter that doesn't have the group delay distortion issues in band would be advantageous, and some real expensive receivers will do things like that. All right, and then the last thing on the list is FM detector linearity. All right, so this block here. So if you were to look at for a quadrature detector, which a lot of people are using these days, and realistically most any detector, if you plot the voltage that you get on the output, remember the detector turns deviation into volts. So if you got deviation on the x-axis and volts on the y-axis, you get a curve like this. It's kind of like a sine wave, actually. And so you hope that your desired band, carrier frequency plus or minus 75 kilohertz for the broadcast band, would be on this relatively flat region of the curve here. And when I say relatively flat, it's not completely flat, because the typical distortions for the quadrature detectors are on the order of 1%. So this is not perfect. And don't forget, there's going to be some distortion from the transmitter too. So even if your receiver is perfect, there'll still be some distortion. So if you're thinking seriously about this number right here, just forget it. It's not a realistic number, nor do you need it, and it may do more harm than a receiver. Some people, for instance, prefer vacuum tube receivers that would have distortions several percent, 2 or 3, 4, 5% distortion, and they would prefer the audio quality from a vacuum tube audio amp than a bipolar amp that might have this kind of distortion, just to give you an idea. Now, I think that's about all I wanted to say on distortion, except maybe just one more thing. There's a spec that you wouldn't see this on consumer equipment, but it's SINAD. I just want to mention this: SINAD. Now, what does that stand for? It stands for signal to noise plus distortion. That's what that means. So rather than measure SNR, it's S over N, noise plus distortion. All right. And if your audio is well designed, you really be just looking at S to N. But the way what you end up measuring when you measure S to N is you're measuring the noise and the distortion. So that's a spec that you'll see sometimes SYNAD, like 12 dB SYNAD, for instance. You adjust your audio level for 12 dB SYNAD, and then that's your sensitivity. That's something that we used to see in commercial receivers. Okay. Now, for our little sensitivity example, we use 40 dB SNR. Okay. And we weren't rolling the distortion into the sensitivity measurement. I guess, obviously, if your distortion is bad enough, just like hum and noise, we're presuming if you're looking for 40 dB SNR, that your distortion is good enough so that it doesn't limit that. But that's, I think, enough said on distortion. And now we can talk about some of the specs relating to interferers. Okay, let's talk about desensitization. It's a receiver specification that is the first one of the receiver specifications we've talked about that will involve an interferer. And so desensitivity degradation due to the presence of an interferer. Usually the interferer is going to be close in frequency-wise to the desired frequency, many times on an adjacent channel. Would be the where you measure descent. So it could be an alternate channel. So what is descents to start with? It's measurement of sensitivity degradation created by a high-level interferer close in frequency to the desired signal frequency, often in a channelized band. It's on an adjacent channel. Okay. Now, you'd have to read the specification for exactly how to do that test. How much sensitivity degradation are you looking for? And in some cases, you may have a fixed level of interferer that you apply, and then you have to maintain a certain level of performance. In other cases, you may increase the interferer until you get a certain amount of degradation. So you have to read the specification carefully to find out how to do the spec and actually put numbers on it. Okay, now just a brief, what blocks in our block diagram are we going to be paying attention to here. The IF selectivity block maybe makes sense if you're relying on filtering to filter off interferers and you don't have the right amount of filtering, you're going to be in trouble. But what might surprise you is that this oscillator right here is very, very important also. So, all right, so let's just continue on. The first and most obvious block is the IF selectivity. Without the selectivity, the adjacent channel descent performance would be the same, or very similar to performance with an on-channel interferer. In other words, if you just put the interferer right on top of your desired signal, and of course, that's going to cause severe degradation. And in fact, wideband FM exhibits a capture effect where it takes where if you have two signals coming in on the same frequency, if the stronger one wins, and it doesn't have to be that much stronger, maybe a couple of dB stronger, and the stronger one will capture the weaker one, and you won't even know the weaker one's present. So if you don't have selectivity, then your adjacent channel interferer would cause a similar performance degradation as if it was on channel. Again, this limiter right here is the reason why you have that strong of a capture effect. It's the gain suppresses the weaker signal, and that, I think, maybe just take that at face value for now. If you if you want to have a stronger or a bigger descent spec, then you have to have more selectivity, and that may be a little bit of common sense there. I want to mention something just about this capture effect. Sometimes that's good. Capture effect is good. For instance, in FM communications, like for police and fire and stuff like that, the you can have skip coming in from other states that completely does not affect the desired communications, because the stronger signal just obliterates it. So you don't even know that you're receiving interferers from that might be you coming in from another state that you shouldn't even be listening to. That is the plus side of capture. The minus side is that aircraft communications, they do not use FM specifically for that reason, because with an AM receiver, if you have two people on the same frequency at the same time, you get some indication that your communication is garbled and something was wrong. And with an FM communication, you might not even know that you missed something. Okay, so because it only takes a couple of dB and whatever stronger wins. So in aircraft communications, they do not use FM for because of the capture effect. Just a little aside. So again, selectivity is important, and I have seen FM receivers that have 90, 95 dB IF filter selectivity. Okay, so you can pretty much if you have a filter that's 10 kilohertz bandwidth, 10 or 11 kilohertz bandwidth, and has 95 dB selectivity by the time you get to the adjacent channels center. That's pretty impressive selectivity. So if you have a receiver with bulletproof selectivity, let's say, are you out of the water? Or out of the woods? Do you have anything you need to worry about? And the answer is yes, you do. You can still be in trouble in terms of descent performance. So let's consider just this little block diagram right here, where we have our desired signal, FM modulated, and our interferer, and we're summing those two together somehow or another. And then there may be an amplifier stage here, but there is a mixer that's involved at some point in the block diagram. And that mixer is going to perform a frequency shift. And the injection to this mixer is from this local oscillator here. And so let's look at some of these signals in the frequency domain. All right, so this right here, our interferer is a tone. So that looks like a spike in the frequency domain. And it may have some phase noise on it, ideally not too much, but every source has some phase noise on it. But we're going to ignore that for the purposes of this analysis, and so we have a good signal generator. So it's strong. It's a strong signal, and it's unmodulated, or at least not intentionally modulated. And then the desired signal is a weak signal that is FM modulated. And so it might look like this, kind of. All right, so it's spread out over the allocated bandwidth. And you notice you don't see any carrier there, because the energy in the carrier has been kind of distributed across the band, because FM is a constant power modulation technique. So with no modulation, your power is all in a spike like this, just an unmodulated carrier with 75 kilohertz of deviation. You're going to have a lot of little side bands that where your energy is all distributed across those side bands. They're not all equal in amplitude, The carrier, you know, there'll still be something there usually, but it's not going to be big, and the carrier may well be smaller than some of the sidebands. How many sidebands do you have? If you have 1 kilohertz modulation frequency, they're every 1 kilohertz, so you'd have a lot of them. If you have a higher modulation frequency, these little sidebands are farther apart. If you have 15 kilohertz modulation frequency, they'd be 15 kilohertz apart. So don't dwell on that. But just this little picture here kind of shows you what you might see on a spectrum analyzer. This is your desired weak input signal, FM modulated with a strong interferer on the high side. All right, now, and of course the interferer could be on the low side too, but just for this example, we're putting it on the high side. And maybe relatively close in frequency, maybe on the adjacent channel. So that if this was 200 kilohertz here bandwidth, this might be 200 kilohertz away from the center of the desired. Okay, and then we come over here, and what does this look like in the frequency domain? Well, this has phase noise, as does every source, and I have chosen to kind of magnify it a little bit and show what you might see on a phase noise measurement test equipment. And so you have the tone right here. This is what you want, the tone, a spike, but it's got some a little Christmas tree around it of phase noise. And so the close-in phase noise is this stuff here, and then the phase noise we care about is this stuff out at an offset, whatever this offset is. We care about the phase noise at that same offset from the center. Okay, and I'm trying to show you why in a minute here. So now I wrote a little text here. The second receiver block, which affects descent's performance, is the oscillator phase noise. Modulates a strong interferer, which raises the noise floor in the receiver IF. An ideal perfect mixer does not fix this problem. This is not a mixer problem. It's an oscillator problem. You cannot fix this phase noise problem by putting in a perfect mixer. All right, so what's the math here? Real quick. Product of two cosines. We're going to assume that each of these is this is an unmodulated cosine. This is a modulated cosine, and then this is a noisy cosine. And so the math here is we have the product of the product of two cosines is equal to half the cosine of the sum plus half the cosine of the difference. Now we're going to throw this term away because it gets filtered off by the IF filter. This is the term that we care about. I'm not keeping track of amplitudes here, so this 1/2 you can kind of ignore it for a moment at least. This is the part we care about. Notice that inside these parentheses here is A minus B. That's everything that's in the argument of this cosine, and everything that's in the argument of the second cosine ends up inside this parenthesis here. So our desired is cosine of the difference. This A minus B gives us a frequency difference. That's why we're doing the mixer, is to form the frequency difference. So this is omega LO. That's the omega for the oscillator, minus the omega C. That's the omega for the desired frequency. That's our frequency shift term. But we also get the phase noise from the oscillator and the modulation from the desired. Now, both of those are that you get those two, not just the difference of the two cosine frequency-wise. And so we have a frequency modulated tone now. Our frequency modulated tone is now not at FC anymore. It's at FLO minus FC. That's this. And our interferer, which was here, relatively unmodulated, is now at FLO minus FC minus the delta F between these two, with the phase modulation on it from the oscillator. So this is what you'd see in the mixer output spectrum right here. You see your desired signal that you want, and you see the interferer, which you would certainly expect to see. You're counting on your IF filter to pass this and reject that, but guess what? You got this phase noise right here. All right, now you also have phase noise on the desired. Notice the desired has the phase noise also, but that would be the close-in phase noise. And I tried to show a little bump right here in the middle from this close-in phase noise. Doesn't do very much to the desired signal because that phase noise is covered over by the modulation. Does affect it a little bit. When you do your hum and noise test, which we talked about in a previous section of this video, then you don't have the interferer anymore. You turn up the amplitude of this guy, and when you turn off the modulation, that's all you've got is the close-in phase noise from the close-in phase noise from this close-in phase noise right here ends up modulating your desired signal. That's what you're looking at when you measure hum and noise with a strong desired signal with no modulation on it. However, we're not using a strong modulated signal here. We got a weak modulated signal, and we've got modulation on it. So the modulation kind of covers over whatever little phase noise, close-in phase noise impact that would have. But here on the interferer now, this phase noise right here, the stuff that's on the same frequency as the desired signal is on after you go through the mixer. That's the phase noise that's in this window right here on the oscillator, is the stuff you care about. And if I raise the amplitude of the interferer, I shift this up and down, and if I make the interferer big enough, I can make this noise right here equivalent to where it covers over the desired signal in the IF at the mixer output and desensitizes my receiver, desensitizes the receiver. It makes the noise floor higher and to where I need a stronger signal to be able to get my receiver to work. So it's desensitization, and it's from the phase noise on the LO, the local oscillator, and not the desired, not the close-in stuff. The close-in stuff doesn't matter on the interferer. It's the stuff on the skirt, which is down a lot in dB. That's the good news. But if you want to have a strong interferer, then you can always make it a problem if you make your interferer strong enough. So this will do an end run around a receiver with lots of IF selectivity, where you'd be, you think you're in River City, you got it all covered because you got lots of selectivity in your IF filter. But if you don't have a good oscillator with low phase noise, if I make this phase noise lower, then I can raise the interferer higher before that phase noise will cover over my desired signal here. And I hope that explains just kind of qualitatively with a little bit of math what goes on with descents and due to phase noise. And I'm telling you, if you read textbooks on this, they'll go into, oh, you got multiplication in the time domain, and that's convolution in the frequency domain. And I'm telling you what, uh, you know, it's really, it'll make you think you don't even understand anything, when it's really quite simple how this phase noise ends up on this interferer, which didn't necessarily have phase noise on it to start with, due to this mixing process. And the arithmetic is right there. Just the difference frequency here, and that the difference frequency is generated by this term, and also the phase noise that's on the LO ends up on the difference, because it's not just the frequency that you take the difference of, it's that whole argument of the cosine here. Everything, phase noise included. Just like the modulation here gets translated from the desired signal, gets translated down here, the phase noise gets translated to a little bump right in the center. In this case, the phase noise on the LO ends up on the interferer, and because the interferer is big, this skirt is now not insignificant compared to the small desired signal. Again, big receivers or good receivers tolerate strong interferers when you have a weak desired signal. Okay, and this is an example of how you can get in trouble due to phase noise. So the super heterodyne receiver, which is what we have here, is a beautiful, wonderful thing, but it does put a lot of weight on that oscillator being a good quality oscillator from a phase noise perspective. Okay, and that, I think, is it for this video, this segment of the video. Now, let's talk a little bit about intermodulation, or IM. Okay, most often when people talk about IM, they're talking about third order IM, sometimes also called IM3. There's other orders of IM, IM5, IM7, but most of the time people talk about IM, they talk about IM3. And then intermodulation is the process. How do you characterize it? Often characterized by input intercept point, IIP3, or output intercept point. So there's different acronyms for that, IIP3 or IP3I or IP3O for output intercept point, third order. So don't get too hung up on the terms. It's called a lot of different things. But again, you're going to characterize it in your spreadsheet, your receiver design spreadsheet, by intercept point. And then IM is the process. Of course, we did a video on that, on what is IM and how do you characterize it. Again, it's caused by imperfections in amplifiers and mixers, and the fact that the transfer function is not a straight line like it's supposed to be. It's got a little curvature to it, which leads to it's distortion, and one of the things that happens when you have distortion is intermodulation. All right, so again, intermodulation provides a mechanism for interferers to degrade your received performance. And remember, the real challenge for a good receiver is not just to receive a weak signal, but it's to receive a weak signal while you're while you have strong interferers present. All right, so maybe you've if you're learning the hard way here, so to speak, maybe you found out that, oh my goodness, I need selectivity, or I'm going to be in trouble. So you put in lots of selectivity, and then you realize that, oh my goodness, I got to have good phase noise on my oscillator. So you put in a perfect oscillator, or at least entertain putting in a perfect oscillator. And then guess what? There's still another mechanism that can get you in trouble here, and that would be the intermodulation process. So intermodulation, it requires two interferers, so it reduces the probability of this happening. If just a one interferer situation is much more probable than a two interferer situation, but in environments where kind of a channelized kind of a band, for instance, if where it's a kind of a setup for interferers at multiple interferers, and I think probably the worst case is like cable TV, for instance, where they used to cable around uh, a coax cable that would run into everybody's backyard. That they would have hundreds of TV channels, all equally spaced, and that amplifier had an intercept point was a big deal on those amplifiers. Uh, Not just two interferers, but lots of interferers, all equally spaced. So, but anyway, for sure you got to have at least two interferers, and they have to be spaced properly. One at some delta F or delta omega, and one at 2 delta F or 2 delta omega from the desired. Either side, doesn't matter. Well, you can be below the desired or above the desired. All right, so the interferers can be close in to the desired, maybe adjacent channel and alternate channel, but they do not have to be. So, for instance, if you're talking about a broadcast FM receiver, you could have an interferer on the adjacent and an interferer on the alternate channel, um, or you could have one that was 1 megahertz away and another one 2 megahertz away. That would also IM, or one 25 megahertz away and the other one 50 megahertz away, and still IM, and cause problems. So let's see. In the field, of course, the interferers will be modulated, probably, almost certainly modulated, and they won't necessarily be equal amplitude. Why that would be improbable for your interferers to be equal amplitude, but and when you test it, then you're going to have probably unmodulated tones and probably equal amplitude tones. So here might be a setup that would be relevant for IM tests. Unfortunately, you had to have 3 signal generators, and so you have some desired signal cosine omega CT plus the phi m, where that phi m is your modulation, the desired modulation if it's FM, for instance. So cosine of left parent omega CT plus phi m right parent. Now, frequency modulation, don't get hung up on the fact this looks like phase modulation. Everything inside the argument of the cosine function has to be phase. Omega c times time would certainly be phase, and then phi m is phase also. Don't get hung up on that. You can express frequency modulation as phase modulation. The frequency modulation does not necessarily have to be in this term right here. It can be, but it can also be in the phase term, because phase is the integral of frequency, or frequency is the derivative of phase. And if you forget that, think about the units. Phase is in radians. Frequency is radians per second. All right, so you can figure out which one's the derivative of which one if you're by the units. So anyway, you've got your desired signal that might look like this in the frequency domain. The a lot of little side bands spread out over 180 kilohertz, let's say, depending on the modulation. That's called for in the spec or the standard. And then we have two interferers here, probably equal amplitude. I show those as E int cosine omega 1t and E int cosine omega 2t, where here's your frequency relationships that you need to have here, where omega 1 is omega c plus delta omega, and omega 2 is omega c plus 2 delta omega. All right, so that would look like this in the frequency domain. Then you have one interferer on the high side at some delta f spacing, and then the second interferer at another delta f away from the first one. And then the IM products, the third order IM products, are one of them here and the other one here. This one doesn't do any damage. This is the one that lands right in the center of our desired receive, and you can't filter it out. Once it lands here, it's right on channel, and you've already lost the war past the point where that IM product was created. Is right on channel. And then also the reason why third order IM is kind of ornery is that it's hard to filter off these guys too, because they're close in, or at least can be close in. So if you're talking about like second order intermodulation, well, that's sum and difference frequency. Well, if I take two tones here and take their sum, well, that's double frequency almost, and take their difference, that's close down to DC. So those second order IM products are easy to filter off. But the third order IM product from this guy could be 200 kilohertz away, and this guy could be 400 kilohertz away, and that IM product lands right in band, and you can't, if you're looking at your block diagram of your receiver, you can't filter those two close-in guys off with this filter, because this filter doesn't have enough selectivity to keep them out. Or if it did, you wouldn't be able to get your other signals that you need to get through there. If you could make this filter 180 kilohertz bandwidth, it would have to be tuned every time you wanted to change your frequency. So that would be difficult. That's kind of defeats the whole purpose of the super heterodyne receiver. But this filter can certainly protect that amplifier, because this filter has selectivity at alternate and adjacent channel. So again, your spreadsheet that you use to predict your intercept point will factor that in and give you credit in terms of this stage's intercept point would be improved by the selectivity from this filter, because this filter keeps the interferers away from this stage. All right, so this is why you want to. I would say it's good design practice to at least model your intercept point, because it'll help prevent you from doing silly things like putting 60 dB of gain up here in the front end of your receiver, for instance, where you have a horrible input intercept point, and your spreadsheet would tell you so. Okay. You kind of want to have some gain distributed back here if possible, so that you can use some of this selectivity to protect those gain stages, because you need a whole lot of gain in this receiver, and you don't want to put it all up front, or you'll have a rotten intercept point. And actually, it'll be bad for your desense performance too. We didn't talk about that, but you don't want stages going into limit for interferers that were supposed to be rejected by the filter, or you get gain suppression from that. I guess that's a little hard to go into all of those details in a short video, but let's So we talked about one more thing. This filter here. This filter can't help you from an adjacent channel interferer and an alternate channel interferer, or even one that's 1 megahertz away and one that's 2 megahertz away. But it darn sure can help you if you're talking about TV channel 2 at 50 megahertz, roughly, and TV channel 5 at 72 megahertz, roughly, IMing in this amplifier right here. So I would go so far as to say it's electrical engineering malpractice not to have something right up front. Never mind the fact that if you don't, all you have to do is walk up and touch your receive antenna, static zap that receiver front end, and then that's it. Then it's done. So this guy right here is important, and it reduces your probability of getting creamed by things you're not even thinking about. It's good design practice. Band limiting if possible. Band limit everything if possible. All right, so let's look at a little example here. Again, suppose we have a receive bandwidth 180 kilohertz. Suppose we have a receiver with noise figure 8 dB. Suppose the input intercept point of our receiver is 0 dBm. And suppose we have two interferers minus 35 dBm each, appropriately spaced so that an ion product would land on our receive channel. All right, so how much degradation will occur for our desired receive signal? Again, check the video out on intercept point, IM I should say. And so here is what we know. If our interferers are minus 35 and we're going to have the IM products, IM delta is the dB difference between the IM product and the tone here. So this is the delta is the difference in dB between this guy and that guy. All right, so that IM delta divided by 2, you add that to your tone level, and that'll give you the input intercept point. And we said that was 0, so there's our simple math. And then we can calculate that IM delta is 70 dB from that equation. And if the IM delta is 70 dB, that means these IM products here are 70 dB below the tone amplitude, and that puts them at minus 105 dBm. Now, our receive noise floor is, that's the noise floor in this band right here, is minus 174, that's KT. And check out our noise video if you want a little more reinforcement of that. Minus 174 dBm per hertz, that's KT. And then 8 dB for the noise figure, we've got to add that. And then we got to add 10 log of 180 kilohertz for the number of hertz we've got in our band. And we end up with minus 113.4 dBm for our receive noise floor. All right. So now we have an interferer that adds to that. So if I add minus 113.4 to minus 105, you can't add the dBms. You got to convert each to back to milliwatts and then convert back to dBm again. You get minus 104.4 dBm. And we're going to treat that tone like it was noise. Is it exactly the same as noise? No, but it's a pretty good approximation. You can treat this interferer just like noise and calculate I'll call it a trash floor, noise plus interference. So of minus 104.4 dBm, how much degradation is that? Well, what was our old floor? Minus 113.4. Now with the interferer there, with the ion product there, we're minus 104.4, so we got a 9 dB receiver sensitivity degradation. Now, whatever sensitivity we needed before, we're going to need 9 dB more now with the presence of that tone there. Okay, the presence of that ion product there, I should say. So what so that's our little example on what IM can do to a receiver sensitivity. All right, so what blocks are we concerned about here? All the active stages in the receive path until the interferers are filtered off. Obviously, selectivity up front is good. The more selectivity you have up front, the more protection you have for all the stages that are behind the selectivity. Kind of common sense if you think about it. But it depends on the offset that you're measuring your IM at, too. If you're measuring your IM adjacent channel and alternate channel, then this filter doesn't help you at all. Not that you shouldn't have this filter, but it doesn't help you at all for adjacent channel, alternate channel IM. This filter can help you for adjacent channel, alternate channel, because it's an IF filter bandwidth. So, you use some common sense there, so obviously selectivity up front is good, but if you put a lot of selectivity up front, you'll probably have trouble with your noise figure. So that's why you want a spreadsheet to keep track of what your noise figure, your cascade noise figure is, and what your cascade intercept point is. And then you can also see at what levels the different stages go into compression, and just make sure that you're not you don't have some stage up front going into compression too early. All right, so mixers are notorious because we ask them to be linear and nonlinear at the same time. It won't mix if it's linear, but then we want it to be linear in terms of intercept points. So, and then lastly, track your intercept point with your spreadsheet. And I guess that's it for this video, this segment. Let's talk about receiver spurs, or receiver spurious rejection, I guess. This is going to be our last interference-related receiver specification. And so what are receiver spurs? Well, they're discrete frequencies where an interferer causes sensitivity degradation. And they can be close to the desired frequency or far away. And every receiver has tens of them, but many are good enough to be unmeasurable, higher order ones. They may be covered over by other degradation mechanisms like descents due to sideband noise, oscillator sideband noise, for example. And so if you were just sweeping a signal generator across all, everything from DC to daylight, just looking for places where you have receiver sensitivity degradation, eventually you're going to be limited by oscillator sideband noise or compression of stages, and you may not ever find some of the spurs that are theoretically there. Okay, so there's just that's kind of a high class problem if you can't find the spurs, or you have a real bad oscillator and the sideband noise is awful. All right, so commercial receivers will often have a spurious response, a rejection specification, and problem spurs may be called out specifically. For instance, they might have a spec that's worded like the spur spec is 90 dB above the sensitivity spec, except for maybe one spur, which is 75 dB above the sensitivity spec, and they'll tell you what frequency is that. Okay, they could word a spur spec like that. Now, how would you measure it? Well, generally you're going to require two signal generators, one for the desired signal, one for the interferer, kind of like descents. Okay, and this guy's on channel, and it's going to be set up for some kind of receiver performance that they would tell you in the spec. All right. And then you're going to hunt around and find a spur, for instance, and then adjust the level of the interfering generator to for the specified amount of sensitivity degradation. And then, of course, you're going to want to read the specification carefully so that you do the test the way that they tell you to do it. Otherwise, the number you get won't mean anything for all receiver specs and specs in general. All right. So now, if you don't have a spec, or if you're maybe just characterizing something for yourself, or someone asks you to investigate something and you do a spurious measurement, and then you'll have to tell them what exactly you did. For instance, if you're doing a broadcast FM receiver, let's suppose maybe you set up your desired signal generator here with 1 kilohertz deviation, 1 kilohertz modulation frequency, 75 kilohertz deviation, maybe, and you adjust for a certain signal to noise ratio here at the output, maybe 40 dB, let's say, like when we talked about the sensitivity spec. And then you would maybe increase the level of this guy by 3 dB above whatever that sensitivity level is, and then raise the interferer on the spurious frequency so to degrade performance back to the same 40 dB signal to noise ratio you started out. Now then you would report that what was the level of the interferer, and you would report that you had degraded sensitivity by 3 dB. And by the way, you want to make sure that this generator is a pretty good quality generator, because if it has a sideband noise floor that is high enough, this receiver can be perfect, and you'll just be looking at degradation due to the sideband noise on the interfering generator. So to measure high performance receivers takes high performance test equipment, unfortunately. All right. So anyway, one of the big blocks that you're going to want to pay attention to when you're looking at mixer or spurs, receiver spurious, is the mixer. This guy right here. So mixer spurs are identified very often by an ordered pair, MN. Some mixer manufacturers may even provide a table with M 1 to 5 maybe for the rows, and N 1 to 5 for the columns. Of course, that'd be 25 cells in that table, and then dB rejection values in the body of the table for each spur. Higher order spurs will have higher rejections. Not all mixers are the same. Balanced mixers can offer more rejection for even order spurs. So for instance, the 2-2 spur might do better in a balanced mixer than in an unbalanced mixer. And so, just the question is, what's the manufacturer willing to guarantee? So that's, your job as designer to pay attention to what the mixer is specified to do. All right. And, for intercept point too, by the way, intercept point, conversion loss or conversion gain, noise figure, all of the metrics for a mixer, you're going to be, when you choose a mixer, you're paying attention to that. And, the data sheet. Now, you may make your own mixer, or you may buy one, and that's your choice. All right. What do we mean? What's the spur arithmetic associated with this ordered pair MN? Now, there are 2 spurs for each ordered pair, and here's the math to determine the spurious frequency. So M times F spur minus N times F focal oscillator, or LO, or injection, whatever you want to call it, equal plus minus FIF. Okay, so how about some examples? Take the 1-1 spur. It's pretty easy one, pretty easy math there. So 1 times F spur minus 1 times FLO equal plus or minus FIF. I think you can see immediately that one of these two spurs is the desired conversion. The other is known as the first mixer image. Both of them are 0 dB spurs, no rejection, and none of them are mixer problems. These are a perfect mixer does both of these, and it's not a problem. You're not going to find a mixer that doesn't do this. You might find some image canceling mixer techniques, but you don't see them very often. Okay, so anyway, the broadcast FM receivers have high side injection, so the desired for the broadcast FM receivers with the minus sign. The other one is the first mixer image, and that is with the plus sign there for the IF. Okay, both of them are 0 dB spurs, no rejection. All right, what about in general the 1N spurs? All right, the 1-1 spur we talked about. Okay, the general case 1N spurs. So F spurious minus N FLO equal plus or minus FIF. Of course, there's 2 spurs for every N. These spurs will be 1 IF frequency either side of every LO harmonic. And they can be pretty bad with the 1-1 image at 0 dB, doesn't get any worse than that. And the 1-2 usually is 20 dB or so rejection. Not very, pretty bad. For 1-2 spur is pretty bad. So, and by the way, for those of you that are sample data people, this particular process right here, you would call this aliasing. Basically, you got something that's up around the third harmonic of your clock that ends up aliasing down into the between minus Fs over 2 and plus Fs over 2. The same thing as mixing. Now, as one final example, how about the 2-2 spur, half IF? Now, this would be a 4th order spur, because 4th order mixer nonlinearity to do this. And you'd expect maybe if you have a balanced mixer, you might do 75 dB on this, maybe 65 if you don't have a balanced mixer. Rejection on this because it's a 4th order spur. Here is your arithmetic for it. 2 times the spurious frequency minus 2 times the FLO equal plus or minus the IF frequency. If I divide through this whole thing by 2, I get that Fs minus FLO equal plus or minus 1/2 of the IF frequency. All right, now a little example. Let's suppose we have a broadcast FM receiver with a 10.7 IF, and our F desired is 88 megahertz. So there's F desired there, 88. Here is 108, that's the upper band edge. Here's our injection frequency, 98.7 megahertz, because 98.7 minus 88 is 10.7. That's our IF frequency. That's our desired conversion. And again, on this picture, where would our first mixer image be? Our first mixer image is going to be 10.7 megahertz higher up here at 109.4 megahertz, barely out of the band. But that's not what we're talking about here. We're talking about the half IF spur. The half IF spur is 5.35 megahertz on either side of our injection. And so one of them is at 93.35. The other is 104.05. Okay, there's the 2 half IF spurs there. Both of them are in band. Both of them are in band. Now, that's just mixer. what about spurs on the mixer injection, the signal that you put into the mixer from the oscillator? What if there are spurs on that input? Well, an ideal perfect mixer will appear to have two spurs for each injection spur, and the severity of those spurs will be determined by the dBc level of the injection spur. All right, so how about an example here? How about an example? Suppose, and I don't know that I've ever seen anybody do this, but just take our broadcast FM receiver again, and suppose our RFN desired is 89.3 megahertz, which if we have a 10.7 IF output, we need an LO of 100 megahertz exactly for that. So 100 minus 89.33 equals 10.7. That's our desired signal arithmetic. Now, let's suppose we choose to get this 100 megahertz by doubling up a 50 megahertz source with a doubler. And of course, then we're going to need a bandpass filter after it to clean up all the garbage coming out of the doubler. And it's highly likely that the 50 megahertz output here will be more than the desired 100 megahertz. So we're putting a lot of, strain on this bandpass filter here to clean that signal up a little bit for us. And let's suppose the end result of this is that we have 50 megahertz at minus 30 dBc and 150, which is the third harmonic of the 50 meg input, at minus 50 dBc. So that's just to suppose. So dBc means dB below the carrier. So whatever the level is of this desired here, this 50 megahertz is minus 30 dB below that, and the 150 is 50 dB below that. Now, so what kind of spurs are we going to get out of our, let's assume this is an ideal, perfect mixer, as good as you can get. And now, what kind of spurs are we going to get out of that this mixer? All right. First of all, the image at 110.7 meg, that's 0 dB rejection to the image, and the that's slightly out of band, because 108 is the upper band edge. So 110.7 is out of band. And yeah. So and then I'm sorry. The other two spurs are 10.7 megahertz either side of 50, and 10.7 either side of 150. So here's the four other spurs that we get, and these two, the ones that were created by the 50 megahertz spur, are minus 30 dB rejection, and then these two will be 50 dB rejection, determined by how bad this spur is on the injection. So what you might be able to see here, just kind of get a little warm fuzzy, is suppose I make this spur better. I do something to reduce the level of the spur. As I do, my rejection here is going to improve. And if I improve the spur enough, eventually I'll be down to the level where oscillator sideband noise is the what determines what happens if I put in energy at these two frequencies right here. My rejection will improve as I reduce the level of this spur until oscillator sideband noise here coming out of this bandpass filter limits how much larger I can make the spurious frequency input. Again, but just to show, oscillator spurs are very important, as are the harmonics on the oscillator. If I don't even have any spurious, suppose I don't have 50 or 150, I have just 200. and just 200 megahertz, which would be the second harmonic of just the oscillator itself. If I didn't have this multiplier in there, I didn't have these unusual frequencies, I just had 100, 200, and 300 just harmonics, then these 1N spurs we talked about up here, it doesn't do you any good to have a mixer that has a lot of 1-2 rejection. If you've got the second harmonic of your injection that you put into it be 20 dBc. That makes sense? I could have a perfect mixer here. And if my second harmonic on my LO is minus 20 dBc, I'm going to have 20 dB rejection on the 1-2 spur. So again, why it matters and what you as a designer need to be thinking about when you design a receiver, like where your spurs going to be, and where are they going to be, and then the ones you care about, and what you're going to do about them. All right, so I think lastly, we need to talk about what are the blocks that we care about here when we're concerned about receiver spurious rejection. Of course, the mixer, the RF filter in front of the mixer. This is super, super important, because if you don't let the spurs get to the mixer, you don't have to worry about what the mixer is going to do with them. Now, practically speaking, you're not going to have a bulletproof mixer. You're not going to have a bulletproof RF filter. So you design so that the spurs you care about, you use some of this and some of that to get to what your spurious spec needs to be. RF filter, mixer for sure. Injection filter here, this filter right here. Obviously, if you're concerned about spurs 1 IF frequency on either side of harmonics of the oscillator, there's your fix right there. All right, so you need to clean up your injection. And by the way, this can also help for noise also, depending on how much what kind of power level you need into your mixer. If you have a lot of gain here in this injection amp, you can have noise issues that this filter can help with also. Not going into that right now, but again, injection filter, and of course the oscillator and the oscillator's power supply. Oscillator's power supply may be even more important. Heaven forbid you've got a switching power supply switching at 300 kilohertz, and you've got 300 kilohertz spurs on the power supply to the oscillator. And what do you think your D-sense is going to do? You're going to have spurs every 300 kilohertz as you move away from your desired frequency associated with the oscillator getting modulated by its power supply, and so that's going to be bad. Now, the last thing I want to mention is just the design. All right, so naturally, given the design, you choose the best components that you can get. But if you're really bad about choosing design, like they were when they designed the broadcast FM band, you set yourself up for failure. And here's an example how you set yourself up for failure. You design yourself a 20 megahertz band here, the broadcast FM band from 88 to 108 meg, with a 10.7 megahertz IF, so that the first mixer image is virtually in band. When I go down to the bottom end of the band here, 88 megahertz, I tune my receiver to 88, my first mixer image is 21.4 megahertz higher than that, which puts it at 109.4. And 109.4 meg is virtually in the band. There's no way I can construct a roofing filter here to protect my receiver front end that can protect me from the first mixer image based on this. I'm going to use the term bad design right from the get-go. Now, I had a reason for doing it. I'm not going to discuss that here, but holy smoke. you can make a very strong case for why this I frequency should have been 35 megahertz instead of 10.7 megahertz, just to get that image farther out of band. You got a chance to fix it. And so what did they do? What is the fallout of this? So that you can make this filter a little bit narrower so that it actually can do something to help you with your first mixer image rejection. They made the filter narrower, but now you have to tune this filter as you tune the receiver. And when I tune receiver down to 88 megahertz, this filter tunes down to 88 megahertz. When I have the receiver tuned to 108 megahertz at the other end of the band, this filter has to tune to 108 megahertz. So this filter tunes along with the oscillator when I change the frequency of the receiver. And it doesn't get very much. It's pathetic how little image rejection this filter provides, but it's all they could do to get some image rejection is to take a one pole bandpass filter and tune it across the band as you tune the receiver across the band. Now, when you tune the receiver, it's actually tuning based on this, tuning the oscillator, but you need to tune this too. All right. So again, design is also important, and good blocks and a good design make you a good receiver. All right. So that's it for this little segment. Well, everyone, if you've been able to stay with us this far, then you're quite a trooper. It's been a long video. So we talked quite a bit about, what a receiver is. Most of the time was spent on receiver specs. We covered but a little bit up front, a little bit of an introduction on what a receiver does qualitatively. And then we discussed 3 specs: sensitivity, hum and noise, and distortion, that don't deal with and interfere, just single input to the receiver. And then 3 more specs: desense or desensitization, intermodulation, and spurious rejection, that deal with a desired signal and a interferer. And so hopefully you get some maybe perspective on things that you need to be thinking about if you're working on a receiver. Not quite enough maybe to start banging out receivers, but stuff you need to be thinking about, what blocks affect certain specs, and we did discuss that. So thanks for watching. And please feedback. You don't like something, speak up, and we'll see you on the next one.